Hi, this is Kumar Singh from Design Analytics LLC and you are watching another episode of Throwback Thursday. Well, today we are actually going to review a very important paper that laid the foundation of a key segment of statistics, I will say, right? Probability theory and a significant portion of, I would say, the underlying aspects of some of the key AI algorithms as well. We are going to review a paper that laid the foundation of Bayesian statistics by Bayes, of course, right? So, as you may know, Bayesian statistics plays a foundational, right, and increasingly critical role in modern AI algorithms, right? But before AI became the buzzword, it was playing a key role in statistics and probability already, right? So it's built on Bayes' theorem, and today we are going to discuss the seminal work in which that theorem was proposed, right? So as you can see here, this is the original paper titled An Essay Towards Solving a Problem in the Doctrine of Chances. Kind of a long name, right? It's a research paper. Now, note that the paper was not actually published by Bayes, right? But it was published by, I think Richard Price was the name of the author, and it was published after Bayes had died in 1763. So, Price was a mathematician and theologian, I think. So he edited Bayes' essay and published it. He also added a very lengthy appendix in that essay explaining implications and applications of it, and he actually even interpreted it to support arguments for rational belief in divine design and inductive reasoning, right? Basically, in a nutshell, the paper intended to mathematically answer the problem that given the number of times an unknown event has occurred and failed, what is the probability that the chance of its occurrence lies within a certain limit? If you wanted to simplify it in simple terms, the question, right, the problem could be summarized as how should we update our belief about the probability of an event after observing it succeed or fail a number of times, right? So, what were the key contributions of this paper, right? Number one, it gave us Bayes' theorem, the foundational form of Bayes' theorem, right? So it introduced the principle of inverse probability, right? So even though it was not written in modern notation, Bayes formalized the prior belief aspect, like before seeing evidence, the likelihood, right, of the data given the belief, the posterior belief aspect, right, updated belief after seeing the data. The second contribution was the geometric approach. So it used a uniform prior, right? So equal belief in all possible probabilities between 0 and 1. Applied geometry, area under curves, to represent degrees of belief, and it calculated the posterior distribution using integrations over intervals. Use of binomial trials was another key contribution of this paper. So the paper described experiments like tossing a biased coin. So for example, if a coin lands 3 out of 5 times on heads, what's the probability that it's truly biased towards heads, right? So in a nutshell, this essay laid the foundation groundwork for Bayesian statistics, Bayesian inference, decision theory, modern AI probabilistic reasoning. Before that, before Bayes, I would say probability was mostly about known game of chance, like forward probability, right? Bayes was the one who introduced reasoning from effect to cause, a shift from frequentists to Bayesian reasoning. So essentially what that means is that it's not just how likely is a result given a bias, but how likely is the bias given the result. As you know, Bayesian statistics, that kind of was a result of this paper, plays a foundational and increasingly critical role in modern AI algorithms, especially where uncertainty, learning from sparse data, interpretability, and decision making are important. To conclude, let's actually review some of the key areas where this paper actually ended up making an impact, right? Kind of, because this paper was the foundation for Bayesian statistics. Uncertainty quantification, right? So unlike classical machine learning, Bayesian methods naturally model uncertainty. In neural networks, what this means is that instead of fixing predictions, you get distribution over outputs instead of fixed predictions. Sorry. It's vital, obviously, this approach of reasoning distribution over output is kind of applicable over multiple areas, right? From medical diagnosis to autonomous driving, financial modeling, right? Bayesian neural networks, Gaussian processes are examples, right? Bayesian deep learning, right, adds Bayesian reasoning to deep neural networks, and they are really useful when data is limited or noisy. Interpretability and confidence are critical. Examples are Monte Carlo dropout, variational inference in deep nets, Bayes flow for scientific simulations, right? Reinforcement learning is another area where which is heavily influenced by Bayesian statistics, right? So Bayesian reinforcement learning accounts for uncertainty in transition models or reward functions, whatever you like to call it, right? It helps balance exploration versus exploitation more effectively, and is the core idea in Thompson's sampling and Bayesian Q-learning. And there are numerous other areas, right? Bayesian optimization, probabilistic programming, active learning, causal inference, and decision making. But the summary is, this paper published in 1763 actually charted a very critical, charted the path and was like one of the initial milestones of a path, a journey that has brought us, along with many other inputs along the way, to where we are right now in the world of artificial intelligence and technology. Thanks for watching. I will see you again actually next week.